So from the process-oriented view, now we are going to discuss the object-oriented view. And there are multiple ways to do object-oriented modeling in the discrete event simulations. And we are going to talk about these error automata this week. So before we start, we are going to position ourselves into a object-oriented paradigm. Okay, I would believe that most of you already understand the object-oriented paradigm because that I'm sure that you are using classes and instantiations and so forth, which are being provided by many of modern programming languages. However, let's see what it really means in terms of the modeling and simulation. So as an example, I'm going to bring up the Akin's problem. So Akin's problem is this. So we have a chessboard 8 by 8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? So 8 by 8. And we are going to place the queen, which is the most powerful object entity on the chessboard. So queen can attack what? Queen can attack the vertically and diagonally, right? So horizontal, vertical attack, diagonal attack, and horizontal attack. It can do in these 3 different ways. Of course, that it can go down and left and wrap down and so forth. Anyhow, so queen can be a very versatile object on the chessboard. So, and now we are going to place 8 of these queens. And we are going to constrain that queen never attack to the other queen. And does this placement satisfies the constraint? Let's see. Okay, so we have one queen attacking no one. Okay, she is safe. And this one is attacking and no one. Okay, and definitely okay, and so forth. You know that I intentionally placed these queens to solve this Akin problem, so it should be okay. Having said that, can you come up with possible solution space which could be feasible or infeasible, that needs to be checked? And possible solution space will be what? So 8 by 8 means 64. And if we place one queen on a certain place, and now we suddenly have 63 empty space, and 62, 61, and so forth. So it's going to be very difficult to search through the whole solution space. And then what? And then we iteratively rearrange the queens in a smart way, ladder heuristics. So that's something that we can do to solve the Akin's problem. And one way of doing such kind of heuristic-oriented rearrangement, we can come up with multiple ways, and also we can code in 2 different ways. First, the process-oriented approach will code it like this. So, okay, this is a pseudocode from a process-oriented perspective. So we have one function procedure solve Akin's problem, and we enter number of queens, and we initialize the chessboard. So we make some array and randomly place the queens. On the chessboard, and then we are going to do a while loop, and then we check the collision on this chessboard between the queens. Okay, and if there is none, then it can break and go away. Otherwise, try to find the colliding queen, 1 and 2, okay, 2 queens. And then as a process, rearrangement process, we need to introduce certain heuristics in here, arrange 2 queens, and put in a something, someplace new, and then we do while loop again. Okay, so we rearrange just 2 queens, and then change it into an adequate place. At least those 2 selected queens does not attack each other, and we do that until we have no collisions happening. Okay. Of course, this is not a complete description of the arrangement, but rather this will require heavy heuristics to find an adequate method of finding a new place. Having said that, okay, this is a one-way of procedure coding which is iterating over and over again, and there is absolutely no class structure here in it. Okay? So this approach focuses on procedure of finding collisions, procedure of arranging colliding queens, and these are not the objects, rather, or composition of functions. Then how to code those A-queens problem solutions, the solution approach from the object-oriented perspective. So to do that, we need to create some objects out of this problem context or scenario. So what we have on this setting is this. First, we need a queen. Okay, so we define class queen, and that class queen will have states. Here, the state is where it is being placed. So here we provide states. Okay, and then we provide behavior. Okay, so this queen can move some other place, some safer place. So let's say move to safe location, okay? This being moved to new location, this being moved to new location, somewhere safe. And then this Boolean function will check whether it is colliding, make a collision with other queens or not, given the context, given the environment, given the other queens, okay? So we provide class queen. And then we want to have a solver, okay, which is a different set, right? So it's being separated, so we provide some entity model. And then what you provide here is a execution model or execution mechanism or execution engine on software or engine. And what we do here is that we define class solver, of course, and then we make this kind of routine, behavior routine. However, it's different from the previous one because then, okay, this is the same and randomly placement is same. However, now what we utilize is that we call upon each of these queens and ask whether it is colliding other queens, and then ask that entity to move somewhere safe. Okay? So here, what we do is that we ask entity to do something based upon its state and some input context if it is going to do certain kind of behavior, right? So this is a complete description of state and behavior mechanism, state and behavior or function. This will constitute a class. Also, this will constitute an entity model. And this entity model, the creation of this entity model, first is the object-oriented approach. And after that, we call upon that entity to do something about it in the process of these scenario executions. And that's more object-oriented perspective. So this approach focuses upon the designing of an object that captures key attributes, here the state, and method, here the behavior and function of the queens. And after that, we invoke object method when being needed, when being called upon, when event occurs. That's the structure of the simulation engine and simulated entity model.